Good morning, mathematicians. Thesis is handed in. A draft has been sent to the committee. They'll read that and we'll see how things go. But it's, I guess, off my mind for a couple days. Actually, that's not entirely true. No, it is off my mind for a couple days. It's just there's a lot of other work I have to do now. Yeah. Yeah. Oh well. That's life. You work and you live forever. That's all there is to it. So, anywho, we're gonna do some quantum today, I guess. Um, Good morning, Jack. Good morning, Boris. Um, yeah, no, some things I'm tempted to turn my attention towards in live stream. I've talked about this a bit already, but yeah, maybe a quantum series live stream, or maybe maybe quantum series. Uh, Maybe trying to understand the art and conjecture. Try to understand known cases of art and um, yeah. There's a few things. What was the other thing I was saying? Oh yeah, the other thing that could be fun is to teach myself differential equations, since I mentioned that's a big weak spot for me. What does it mean to submit a thesis? Well, it means, because in order to graduate with a PhD, you have to write a thesis, and so, but that thesis needs to be approved by someone, and that someone is a committee. So I sent in the current draft of my thesis to a committee, and in 3 weeks, and so they have 3 weeks to read my thesis. Hi, mom. Love you. No, I'm not. I'm not done. I'm not done. The thesis has been submitted, but then my defense is on the 16th, and then there is and then yeah, there'll probably be revisions. Um, can I tell how to compute the eigenvalues of a Mobius string? What? Huh? What do you mean by that? Rod, clarify what you mean by that immediately. Why can we just push the integral inside here? That's what I would like to know. I guess they're independent. Yeah, why is this allowed? Because it's physics? Is this allowed because it's physics? Wow, chat's popping off this morning. Hello, Russ. Hello, QB. Thank you, QBurn. Can I make a tier list of journals? No. No. Of journals? Relative? And where does ant? Wait, ant? Are you talking about journals or are you talking about subfields? Are you talking about journals or are you talking about subfields? Mobius strip, it's a meme, nonsense quantum math line from the Avengers movie. Ah, yes, okay, I've actually heard of this. Yes, I've heard of this meme. Yeah. No, this is actually a problem. I have no idea. I have no understanding of the journal hierarchy. Um, and no one will explain it to me. I don't know how to choose a journal. And no one seems to be able to give me a clear explanation on how to choose a journal. So I just submit everything to the annals. Okay, so we got a product rule, and then the Schrodinger equation says this, and we plug that into the complex conjugate, and then I guess multiply through psi and psi conjugate and add them together. Yeah. Wait a second. Seems like there's some things. Oh yeah, I guess we get some cancellations of terms there. Right, these the terms out here will cancel. Okay. Terms out there cancel. We pull out a spatial partial. We get that. And so the integral is this. But that must go to 0 as x goes to infinity. Otherwise, it would not be normalizable. Okay. Interesting. Okay, that's cool. There's a poor man's annals, which abbreviates to math an, on CVs. Nice. Okay. Let me submit there. At time t equals 0, a particle is represented by wave function. That's a hell of a wave function. Yeah, normalize, sketch that, blah, blah, blah. Yeah. Consider this wave function. Yeah, consider that later. Momentum, baby. Right. The expectation of x should be that. What does that mean? It does not mean... Yeah. Now, as time goes on, the expected... Why quantum physics all of a sudden? Why not? I mean, in part because someone I'm tutoring is interested in physics, in quantum physics. So I'm trying to review some of the basics so that I can tell them not complete nonsense in our next meeting. I mean, I'm gonna have to review some of this off stream, but figured I'd spend some time looking at it on stream as well. For entertainment purposes? Are you not entertained? Right, so we take a time derivative. Why do we take a time derivative of the expected value? Oh, right, knowing how fast it moves. Oh, right, because, right, and I think he says we will only justify later that the expected value of velocity is the time derivative of the expected value of the position. Right. And so it's this. It's this term here. And then if we multiply by mass, we get the momentum. And this is why this should tell us that this is partly why momentum is represented by the differential operator. But I think we need to talk about in order to properly interpret this, we need to realize this is the uh, inner product. Yeah, inner product of operators. Yeah, because I think we're gonna have the general idea right. So the expected value of a quantity should be. Let's bring up my notes here. So the expected value of some I should make new office hour notes. These are getting long. It's going to make things laggy and weird. Bye-bye, office hours notes. Bye-bye. Wow, see, even deleting it made it a little, get a little weird. Office hours. So if we have some measurable quantity, the expected value of that should be the integral. Well, right. It should be, I guess, something like this. I don't know if I'm doing my brackets correctly, but it should be this, which should be the integral overall of space, not overall of time of this. Something like that, right? But maybe physicists have a backwards convention about... right. We apply it to... Yeah, I forget which way. Maybe physicists do the backwards Hermitian product. Well, what I consider to be backwards. I see. But it should be the other way around, I guess. Is there a reason I'm learning quantum mechanics? Because it's cool. And in part, I mentioned a moment ago that one of my tutoring students is interested in quantum mechanics, so I'm trying to review some of the basics. We also got kinetic energy, angular momentum. Right. Calculate the expected value of any quantity. Oh, wait, what? What's going on there? Wait, why is it Q? Kinetic energy is that, sure. So we could just replace that. Angular momentum. The latter, of course, does not occur for motion in one dimension. To calculate the expectation value of any such quantity, qxp. Why is it qxp? I see. So we take right any expression with x and p, and we just replace each instance with p with that operator and then compute. Okay. You don't know how good Griffith's test is, though, at the end? Okay. Tajan's book for more rigorous treatment. Actually, Angela Collier recommends, and I do really like this. What's his name? I forget his name now. What's his name? I think I downloaded it. What's his name? There's another big one I'm looking for. Good morning, Ken. I know. Yeah, Shankar. Thank you, Shankar. Yeah, I absolutely love his explanation of I remember like years and years and years ago. This is coffee. Yes, this is coffee indeed. Years and years and years ago, reading or sorry, watching his YouTube lecture where he drives E equals MC squared. And in fact, I basically just copied that exact same explanation from him and presented that as a talk in our little local grad seminar because I just love that derivation. It's mostly like you just use like with the exception of one Taylor series, you use like basic high school algebra applied to the postulates of special relativity to derive it, and I just love it. I just love it. Um, yeah. So I should probably look at Shankar. Where is do I have Shankar downloaded? No, that's weird. No, that's weird that I don't. Oh, abstruse goose. They they disappeared. It gone for good. Okay, we know this now. Interesting. I remember they disappeared for a few years and then they came back for a brief couple months and then disappeared. Anyhow. What book covers advanced topics in abstract algebra? Depends on what advanced topics you want. I just tell everyone Alufi for your whole undergrad and even into your undergrad and even into your grad. Yeah, Vibel if you want homological algebra, more specifically. Um, you know, Eisenbud Harris maybe. Um, what level of procrastination so far this week? Oh, your level of procrastination so far has been legendary. Well, uh, don't let it get too legendary. Wow, the comic panel that gets more and more relevant as time goes on. Nice. Let's download Shankar actually. This is the good stuff. A new Alufi is for babies. Nerdy Quagsire would know as a baby himself. Review of classical mechanics. That's probably good. That was a mathematical introduction. Interesting. Dotting your I's and crossing your H's. Nice, 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 nice. Wow. I might have to buy myself a hard copy of this bad boy. I might have to buy myself a hard copy of this bad boy. Let's go ahead and download this. Excuse me, that's not how I like to label my documents. What is this, 1984? Was this literally 1984 over here? Let's put it on my desktop. I don't have enough things on my desktop already. Starts QM 115 pages in. As it should be. It probably says in the preface what the prereqs for the book are, but it's too late. I put it away. I'm looking at some quantum now, just for fun. Just for fun. Actually, you know what I should be doing? There's this seminar that I might give a talk about Ramanujan graphs in, so I should probably go read about that a little bit. So that might be tomorrow's stream. I think the next little while, yeah, maybe there'll be some quantum mechanics, maybe there'll be some Ramanujan graphs type stuff. Yeah. Literally 1984. Yeah. You feel like every textbook's preface claims to be self-contained. Yeah, yeah. For Shankar's book? I mean, Shankar has, and I would guess that the barrier to entry in Shankar is lower because Shankar has a whole chapter on Shankar has a whole chapter on mathematical background. Yeah, I think I yeah, there is a very loose my understanding is there's a very very loose connection um, between quantum mechanics and quantum groups. In that, yeah, the groups were born out of the math of quantum mechanics, but it's not like directly applicable. And it makes me mad every time I read about the quantum basis for Heck algebras or whatever. It makes me mad. Yeah. Interesting. I can't find the original explanation that I found, but there's a really cool explanation. I've talked about it on stream before. Um, from Vogan, uh, explaining how the orbit method is just a generalization of quantization, basically. Maybe he explains it here. I mean, basically, the idea. I could even say the basic idea is that the orbit method. The orbit method is about. Why did you go there? The orbit method is about is about um, relating unitary representations of groups to I mean, nilpotent orbits. And these things, or sorry, coadjoint orbits. I mean, they are nilpotent. And these things carry symplectic structure. This is symplectic geometry. Someone was asking me if I know some symplectic geometry yesterday. It's a little bit. And this is what's the word I'm looking for? I mean, this is Hilbert spaces. And so the idea is that the passage between these two worlds exactly mirrors the classical stuff, which is like a sort of symplectic formalism with your Lagrangians and Hamiltonians, and your quantum stuff, which is like the Hilbert space formalization. Hi, I don't know if I can say your username. um, or maybe geometric quantization, not canonical. I don't know the difference. I believe whatever you say, Rod. And nothing what Leo says. He's not here to hear me say that, I guess. There's a quantum book by Peter Voigt, which introduces QM fully from the representation theory point of view. Oh man, I'm getting way too distracted. That is not what I need to be reading to help my... this is just slides. But the slides probably... But okay, now I'm intrigued. This is not what I need to be reading. Quantum theory, groups, and representations. This is not what I need to be reading to help my student that I'm tutoring. But I guess it is what I need to be reading to have a soul, to feed my soul. Oh hell yeah. Hell yeah, Lie groups on page 6. You know you're reading a good book when you see Lie groups on page 6. Very interesting. Very interesting. Linear algebra review in the middle. Nice. Okay. Okay. Interesting. And we got some representation of SU2, SO3. Very interesting. Yeah, I'm gonna have to stash this away for later. I should make a QM book. What am I tutoring the student in? Well, at the moment, we've mostly been doing linear algebra so far. We've mostly been doing linear algebra so far, but they want to talk more about. They're a student in chemistry actually, um, and yeah. What's this book called? Quantum theory. Quantum theory groups and representations. I'll just leave it at that, and then I'll say it's by Voigt. Voigt is the right way to say it, right? Or is it not? Or no? Linear algebra does rock. That's true. It literally is everything. Got some wave stuff, some uncertainty stuff, standard deviation. We'll prove it in chapter 3. That's based. Love to see it. We're doing quantum mechanics. You know what I want to understand? Why is the wave equation... I mean, I guess you just solve it and you just see that these sinusoidal things are solutions. But, you know, it's always strange to me, like, one thing I don't understand... I should ask my roommate about this, maybe good sources for this, but, like, one thing that, you know, I'm always confused about when I go to talks in like differential equations or say finance or something when they're using a lot of differential equations, you know, I'm always lost as to like, they're like, oh, here's what we're modeling, and so here's the differential equation that we're using. I guess it's just something you just pick up, right? You just get used to what sort of differential equations mean what, you know, but it's something that, yeah, I don't know. I feel like I want to understand better. Is like, why is, you know, some given, you know, or there's like, oh, they add the drift term in the differential equation, right? And it's just, oh, they just add some other function that means the drift. I'm like, why is that? Why is that the right thing? You know. Maybe I should have someone. Is anyone in chat a differential equations expert? Maybe I should have a differential equations expert on for like a live stream chat where I just ask them questions like this. Yeah. Letting yourself be distracted by quantum theory instead of studying for topology. I mean, I like having the views, but I would also implore you to log off and study for topology. Yeah, let's see. Time-independent Schrodinger equation. Okay. Talk a lot about a wave function. The time has come to stop procrastinating, and logically, how do you get this in the first place? We need to solve the Schrodinger equation. Amen. Differential equation, diffie x, baby. Oh, hello, Professor Escardoso. Haven't seen you for a while. How's it going? So we need to choose a potential, and we'll start with choosing a potential that's independent of time. In that case, yeah, what's the justification? What's the justification for separation of variables? it's just a guess, right? Like it's not like there's a theorem that tells us, oh, it's just like it's the first thing we try, right? Like how to know when we can use separation of variables in a differential equation. First order, key indicators, no mixed addition, subtraction. Okay. I wonder, is there something? You know, the problem you were working on was from a quantum computing book. You're about to participate in a thesis defense panel on topological quantum field theory. Oh, very cool. Very cool. I submitted my thesis last night. Oh, 3 weeks. 3 weeks from now, I'll theoretically have a PhD. Connections to geometric Langlands. Crazy. That's crazy. You don't know about all differential equations, but in satellite altitude dynamics, the function used to represent drift is based on the estimated gravity gradient of the Earth. But like, so for example, like what I don't understand, and what I don't understand, for instance, is like why, because like there'll be this big differential equation, and then they'll just add a term. I think sometimes it's like beta, and then they just call it the drift, right? And so why is adding a term I mean, I guess it makes sense, because it's like you have a function, and you add some, and that's like it, kicks it off in a direction, I guess. The problem showed that there are no non-trivial maps in GLN that preserve the p norm. No non-trivial maps in GLN? What do you mean by that? What do you mean by that? No non-trivial maps in GLN? What do you mean? Are you just talking about automorphisms of a vector space? What do you mean? Matrices? And what do you mean p norm of what? Of a function on the vector space? What do you mean? You have a graduation gift for me. Well, I haven't graduated yet, so I hope you kept the receipt and can take it back. If I don't. Differential equations and PDEs seem like a box of tricks. Stop thinking and separate the variables, or do some integrable factor or something. What kind of differential equation? I don't know. I've seen this. I've just seen this in various places, and I'm just expressing a general ignorance of. Okay. You're saying, sorry, Leo. You're saying n by n invertible matrices that preserve the p norm of a vector. I see. So, yeah, you mean this thing, and a matrix such that this, right? That's what you mean? Got back to find you're not the only blue here. Not anymore. Not anymore. No, no, no. No, no, no. Cannot always be used. Even when it can be used, it's not always possible to get past the first step. Right. Okay, so it is just a sort of guess and check thing, right? Like maybe there's some theorems out there, but yeah, okay. Um, okay, so we'll just say it's a guess and check thing. So we're looking for solutions. There could be more solutions, but yeah, I think the drift form is an external force. Yeah, but it's just like I guess I'm just trying to explain like the thing that I don't understand. I just have no sense of, no intuition for is like why certain differential equations mean certain things and why adding certain terms correspond to certain like physical things, like there being a drift or some divergence term or something. I just have no sense of this. Where so when I go to these talks and people are like, oh, here's the thing we're studying blah blah blah, and then they're like, so here's the differential equation that models this, and I just like I have no sense of like why that's the right thing. um like I almost like how to like why is the spring what's the equation for a spring, the differential equation for the harmonic oscillator. So like this is an important one, right? So um differential equation harmonic oscillator. Like, of course you could just solve this and see that you get a springy motion, right? But imagine I have a physical situation and I'm trying to invent uh, you know I'm trying to come up with a differential equation that models it, and then later solve that and get the equation that describes the physical situation. And it's just this that I have no sense. So like, why is it the double time derivative plus this is zero? Why should it be this? Um, they either fit reality or they don't, I guess. Yeah, but like how, like isn't the idea that I should be able to model these things, to like isn't the idea I should be able to look at a situation, write down the differential equation that's the proper model for it, and then solve it to find like for example like the like what like we don't know what all the solutions to Navier-Stokes looks like, but for some reason we know that this should be the right thing to model fluid dynamics. But why? You know. Um, yeah, I guess maybe this is where I need to start. I need to go to the lab and see what are the types of forces. I guess, but coming up with differential equations directly is hard. That's why there's Newton-Lagrangian mechanics. The first term is from second law. A force, right? Force should be proportional to displacement. Yeah, I guess fundamental laws like F equals ma. Yeah, I just somehow I want to build up a bigger bigger, I don't know, better intuition. Have you looked at the new Konstevich paper? No. Um, Birational maps from no. I mean, I'm not gonna understand a word of this. Non-commutative, blah blah blah, Hodge, blah blah blah. I have no idea what's going on. I can see its derivation, the harmonic oscillator, in any book with Lagrangian mechanics. I don't think you can post links, the real deal, but if you tell me the name. Yeah, I don't know what any of this is. Motivic Galois groups. I mean, this is beyond me. How about the diagonal matrix? Huh? What? Oh, you mean for that norm preserving problem? Yeah. Yeah. Most differential equations in physics can actually be derived from minimizing the action. So maybe that's where I need to start. Maybe I need to start. Maybe I need to start with classical mechanics and Lagrangians. Like for stuff at the level of fluids, just recently have proved things like limit of classical model converges to differential equations in fluids. The other term you know from lab that there's a force that is proportional to displacement, Hooke's law. Yeah, but I guess I want to understand that. I see. Right, right. So that I'm okay with. I mean, I guess this Hooke's law, right? So I'm okay with starting the print. I'm okay with starting from Hooke's law. But now here's what I want to understand. How do I get from Hooke's law to understanding the differential equation? I mean, I guess force should be ma. So we know that we should have like a time derivative here, right? Um but then in the equation, the harmonic oscillator, there's like a double spatial derivative, right? Or something? No, there's a double time derivative. Oh yeah, acceleration. So there should be a double time derivative. Okay. Okay. So actually maybe I'm good on this now. Maybe I'm good on the simple harmonic oscillator. Actually, this is totally yes. Okay. This is mhm. This actually makes some sense to me now. But you see what I mean? It's just like even these basic things, I just have a lack of intuition. And I guess I just need to spend more times. So like also like why is the wave equation like is there a theoretical way? So if I look at the wave equation, again, yes, we can just test it in the lab, or you could just write down like we know waves can be described by like sinusoidal functions, and so we just write down a differential equation that it satisfies. But then like, you know, I want a more theoretical justification. Is like, so why would we think that it's this? You know, why would I think that it's this? What are my thoughts on topological Hochschild homology? I have zero thoughts on topological Hochschild homology. I just don't know much about it. For instance, do you know that a vector field in a simply connected and nice region, you need to know the divergence and curl of the vector field to completely specify it? You get the Maxwell equations. Uh, okay. I don't know why that's true. I don't know why that's true. Double space derivative is in the string equation, which is like a harmonic oscillator at each point. Yeah, but I don't. But why? I really want to understand why. I want to have a better understanding. Um, but eventually, it's lab and law. Yeah, yeah. But I just need to better connect these things in my mind, right? Like I am now happy with the okay, derivation here. Here we go. Okay, this is what I want. This is what I want. Is this derivation here? Um, yeah. You can also get the wave equation as Laplace equation when the inner product has Minkowski and so. Okay, I mean we're a few steps away from that. Um, um, yeah. Most derivations come from observations of what happens when we vary certain variables in a given event. Okay. Okay, next up. Okay, tomorrow I think we're going to call it here. Maybe I'll look at Helmholtz theorem. Tomorrow I think I'll come back to this page and try and understand the derivation of the wave equation. And also the heat equation. Why is the heat equation the way that it is? These are questions that are on my mind. And then maybe we'll return to quantum mechanics. Yeah. Anywho, QED.